Hello everyone, welcome back to our channel. This is Dr. Lakshmi Tara. So here we are going to see about the fiber optics and the optoelectronics. So in last session we have seen about the elements of the optical fiber communication system. So what are the elements we have seen? We have seen about the transmitter, receiver, and importantly the optical fiber, okay, that carries the light. So what are the transmitters we have seen? We have seen about the LEDs and the lasers, just an overview. And then receivers, so pin photodiode, avalanche photodiodes, and what are the materials which is used for the manufacturing of optical fibers, and how it has been fabricated, that is based on the index difference, and how much mode has been propagated, so based on that single mode fiber and the multi-mode fiber. So these are the overview, just an overview of the optic elements in the optical fiber communication systems. Okay, so in this session we are going to see about the light propagation in the optical fibers. Okay, so how the light has been propagated, just a working phenomenon. Okay, so in this diagram, so what we are going to see. Okay, so what we have inferred from this diagram, so here one media is there, that is N1, then another medium is there. Okay, so this is the basic we are seeing in this diagram. So N1, consider this where we are going to incident the ray in N1. So N1 is the refractive index of particular medium, and N2 is the refractive index of the another medium. Okay, so here we are going to incident the ray in the N1 medium. So this is the normal line. Okay, this is the normal line. So the angle between the normal line and the incident angle is given by the pi 1. Okay, and the refractor angle and refractor ray based on the normal line is given by the pi 2 and pi 2. Okay, so if the angle comes into the picture, so when I incident the ray at an angle, okay, there should be the possibility of bending of the signals or the reflection of the signals happens. So there may be refractor ray has been comes, otherwise reflector rays has been comes. Okay, so if it comes, so what comes into the picture? The Snell's law. Am I right? So what Snell's law describes? It describes how light has been bended or refracted when it passing between the two different mediums. Okay, two different mediums. So it is given as an N1 and N2. That is two different refractive index of the medium. So what is the formula for this Snell's law? N1 sin pi 1, which is equal to N2 sin pi 2. That is sine of the angle of incidence multiplied by the refractive index of the first media, which is equal to the sine of the angle of refraction, which is multiplied by that media. Okay, so the next one is pi 2 is equal to 90 degree. Okay, so pi 2 is equal to 90 degree means that angle of refraction is 90 degree. At a particular angle of incidence, the ray become what? Angle of refraction should be 90 degree. That angle is known as the critical angle. Okay, that angle is known as the critical angle. So pi 1 is equal to pi c. At a particular incident angle, the ray of refraction should be what? 90 degree. So which is given by pi c is equal to sine inverse of n2 by n1. Okay. So here, once we know about the refraction and the critical angle, then the important phenomena is the total internal reflection. Okay, so most of the fibers works on the principle of the total internal reflection. So the light has been reflected completely over the fiber, then only the propagation becomes highly efficient. Am I right? At a particular angle, the ray and completely reflected into the medium. Okay, into the same first media. So how it has been happen? When the angle of incident is higher than the critical angle, the total internal reflections has been happened. Okay, so two conditions are there. One condition is always N1 should be the media of the first media should be that N1 should be always the refractive index, the n stands for the refractive index. The refractive index of the first medium is always greater than the refractive index of the second medium. So n1 is always here in this n1 is always greater than the n2, and the second condition is the angle of incidence should be greater than the critical angle. Automatically there will be the total internal reflection happens inside the fiber. So once we understand how the angle of incidence should be, so how the ray has been reflected or refracted, so then next we need to understand the types of rays. Okay, so we have the meridional ray and the skew rays. The meridional ray is otherwise known as the tangential rays because it passes the axis. The ray ray completely totally internally reflected and it passes over the axis. So it is named as the meridional ray or the tangential rays. Okay, so once we know about the rays, so how the incident angle has, how should be the incident angle, how the next thing is if we incident the light, okay, how it has been propagated over the fiber. Okay, the next important terms comes into the picture, that is the numerical aperture. Okay, so the light gathering capacity of the fiber, that is the numerical aperture. So if you incident the light, to the fiber, how the fiber has been captured that incident light, okay, that light gathering capacity of the fiber is the numerical aperture. So which is given by Na, numerical aperture is given by Na, which is given by n is equal to n sin theta naught maximum, that is the maximum angle. Okay, the maximum angle that has been captured by the fiber, that is known as the acceptance angle. Okay, the acceptance angle of the fiber is the maximum angle captured by the fiber. Okay, then numerical aperture is otherwise given by the formula of n1 sin theta c, which is also equal to, the numerical aperture is also given by the square root of n1 square minus n2 square. We know that n1 is the refractive index of core and n2 is the refractive index of the cladding. So based on the different media refractive index, okay, the numerical aperture has been calculated, and also it is given by the formula of n1 square root of 2 delta, where delta is the index difference. That index difference also based on the refractive index differences between the core and the cladding. Okay. Okay, so we know the meridional ray. So meridional ray that passes over the axis. So the what the next ray have mentioned, that is the skew rays. The skew rays that follows the helical path. Even though it is completely internally reflected, it won't passes over the axis. Okay, it won't passes over the axis, just traces the helical way. So skew rays is otherwise known as the helical rays. So what are the rays we have seen? We have seen about the meridional rays and the skew rays. Okay, so once you understand so about the how the total internal reflection happens, so what is Snell's law, so what is critical angle, so it is easy for us to propagate the light over the fiber. Okay, so what is the numerical aperture, so how the light has been captured, so at what angle it has been captured, so how should be the core refractive index, cladding refractive index for getting the total internal reflection phenomena. So once we understand that, we little bit understand the propagation working phenomenon. Okay, so we can see some of the exercise problem to understand. So what is given here, consider the interface between a glass slab with n1 is equal to 1.48, that is the core refractive index, and air for which n2 is equal to 1, that is the cladding refractive index. So what is the condition have mentioned for total internal reflection? Always n1 should be greater than the n2, that is core refractive index must be greater than the cladding refractive index in order to attain the total internal reflection. Okay, so what is asked here, so what is the critical angle for the light traveling in the glass? Okay, so we know the formula for the critical angle, that is pi c is equal to sine inverse of n2 by n1. So if we substitute the value of the n2, that is the cladding refractive index, and n1 co-refractive index, we can get the value of the what critical angle. It is a very simple problem in order to understand. Okay, so the next problem uses the light ray traveling in the air, n1 is equal to 1, is incident on a smooth flat slab of ground glass which has a refractive index n2 is equal to 1.52. The incoming rays makes an angle of pi 1 is equal to 30 degree with respect to the normal. So what is the angle of refraction pi 2 in the glass? So they have given the value of n1, n2, refractive index of n1, refractive index of n2, then pi 1, the angle of incident. They asked for the angle of refraction. Then it is easy for us, we know this Snell's law. So what is Snell's law? N1 sin pi 1 is equal to n2 sin pi 2. The pi 2 stands for the angle of refraction. In order to find the angle of refraction, so sin pi 2 is equal to n1 by n2 sin pi 1. We know the value of n1 and n2. If we substitute the values, we can get the sin pi 2. Then pi 2 is equal to sine inverse of the particular value, that gives the angle of refraction. Okay, so in order to get the values in the radian format, we know that degree to radian formula. So 1 degree is equal to 0.0174533 radian. Okay. Okay, the next simple problem, so which is consider a multi-mode silica fiber that has a core refractive index n1 is equal to 1.480 and cladding refractive index of n2 is equal to 1.460. So what they have asked? They have asked about the critical angle, numerical aperture and the acceptance angle. So we know the formula. So critical angle, so pi c is equal to sine inverse of n2 by n1, because one angle should be the 90 degrees. So pi c is equal to sine inverse of n2 by n1. They have directly given the value of n2 by n1. So we can substitute the value of n2 by n1 and we can get the values. And a numerical aperture, so we have much formulas for the numerical aperture. Directly they have given the value of n2 by n1. So we can go for the square root of n1 square minus n2 square. There we can get the value of numerical aperture. Then the acceptance angle. So the maximum angle that light has been captured, so that comes under the numerical aperture. So in order to find the acceptance angle, which is equal to sine inverse of numerical aperture, that gives the acceptance angle. So once we find the value of a numerical aperture, it is easy for us to find the acceptance angle, which is what is given here, 14.03 degree. Okay, I hope you have understand the little bit about the propagation of a light inside the optical fiber. Thank you.